The previous video had a number of equations that we solved that involved e to the x and log x. I'd like to do a couple more in this video, especially in context with applied type problems or problems that you may see if you continue on in mathematics. So here is my first example. How long until an investment of a certain amount doubles if interest is compounded continuously at a rate of 10% annually. So 10% is a good historical estimate of the annual growth of the stock market over the last 100 years. So this is something that you can kind of back of the envelope calculate you would get if you invested money in an index fund. Here's the answer. I'd like to know how long it will take $1 to turn into $2. I'd like to know how to double my money. So the amount I'm going to start with in my interest calculation is 1. To calculate interest, you multiply by e to the RT power. Here the rate is 10%. So I'm going to multiply by 0.1 times t. I don't know how many years I need to wait until I get $2. This is a very routine equation to solve now that we're masters of the function log x. All you need to do is apply log x on both sides. Log and e are inverses, they undo each other. And so I will find 0.1 t is equal to log 2 after applying the logarithm on both sides. So dividing by 0.1 or multiplying by 10, I find t is equal to 10 log 2. And if you put this into a calculator or a computer, you could find out that t is approximately 6.93 years, or in about 7 years you will double your money. Let's suppose I was in a hurry and I'd like to double my money in 5 years. So if we need to double in 5 years, then I get the equation e to the r times 5 should be twice what I started with. Here the amount I'm starting with again is 1. So I have 2. That solving in the same way gives me r is 1/5 log 2, which is approximately 0.138. So if I had an interest rate of 13 or 14%, then I would double my money every 5 years. That would mean I'd have 4 times my money in 10 years, and in 15 years I'd have 8 times my money. It's extreme growth. Let's do another type of problem we haven't quite seen in our past. How about if I have the function f of x equals 1 over 1 plus e to the negative x power. This function here is used to model growing things that have unbounded growth. Let me draw you a graph of this function and describe when it could be used. So here's my xy axis, or my x f of x axis. Here's 1/2, here's 1. From our knowledge of e to the x, we know that if you raise e to a negative number, like e to the negative 10 power, you get a number that's extremely close to 0. E to the negative 20 power is essentially 0. E to the negative 1 million power, ridiculously close to 0. It's almost incomprehensibly close to 0. So if I plug in a very positive number x. So if I plug in a number way on the right side of my picture here, e to the negative x power is essentially 0, and I'm going to get a function that's 1 over 1 plus a number that's almost 0. So this is close to 1 if x is big. So I'm actually going to get a horizontal asymptote at 1. If x is big, it's close to 1. If I plug in x equals 0, e to the 0 is 1. So if I plug in 0 for x, I get 1/2. So I cross here. Then if I plug in a very negative number, so if I plug in a number way on the left side of the picture, e to the negative is e to the positive number. That's a very huge answer. So if I plug in a number that's on the left side of my picture, I get 1 over a very, very big number, and 1 divided by a big number is little. So regardless, this is what the picture looks like. It starts out close to 0 here, comes up, it crosses at 1/2, and then starts to level out and tend towards a horizontal asymptote at 1. This model is, say, a population that's growing that has only a finite number of resources. The percent of the population that it's grown to its maximum capacity is given by this graph. So pretend 1 is 100% capacity. That means the population is growing to the biggest it could possibly be. The growth rate might be given by this curve. Or let's say you're a weightlifter. You have your own personal maximum. So you can only say bench press 300 pounds, 400 pounds. Maybe that's the maximum amount of bench press that you could physically lift. When you start weightlifting, you're not very good at it. And then as you train, you get closer and closer to 100% of the maximum weight you can lift. Maybe your progression as you go along on your weightlifting journey is modeled by this function. There's a lot of things that are modeled by this logistic growth function. That's what it's called, logistic growth. I'd like to do an example involving this. Let's say I'd like to find the inverse function. So let's find the inverse to f of x. It has an inverse because it passes the horizontal line test. To find the inverse, what we do is start by letting 1 plus e to the negative x equal y. Next, I will solve for y, and that'll give me my inverse function. So to solve for y, I'm going to divide both sides by y, and I'm going to multiply both sides by 1 plus e to the negative x, and this is what we find. I'm going to isolate the exponential function, so I'm going to have 1 over y minus 1 is e to the negative x. I'm going to simplify and combine these two fractions just for fun. I'm going to multiply the second fraction by y over y. So I believe I get 1 minus y over y is e to the negative x. Now I've isolated the exponential function. I can apply log x on both sides. I get log 1 minus y over y is equal to negative x. Lastly, I'm going to multiply both sides by a negative. If you multiply a logarithm by a negative 1, that's the same as taking log of the reciprocal of the inside part. I'm raising the inside part to the negative 1 power. So I get y divided by 1 minus y. So there is my inverse function. The inverse function is log x over 1 minus x. So we denote that with f with a minus 1 exponent here, which again does not mean 1 over f. Okay, excellent.